wait just a second to see it live on the actual thing on the YouTubes.
I forget which piece of software, but I remember recording a podcast where they do this like local recording, and then later at the end of the recording, everybody's computers uploads it to one person's computer, and then it'll automatically knit everything together. So maybe we can use that next time if necessary.
Hey everybody, thanks for joining us. My name is Diego Salazar, the owner of Cypher Stack and all these wonderful men. No, hold on, wait. I have more to that sentence. And all of these wonderful men work for me, not owner of all these wonderful men. These awesome mathematician, cryptographer kind of guys. This is our first time doing live streaming, kind of our research meeting. So bear with us. We're using Jitsi, which is open source, video conferencing software. And as open source software does, sometimes things are a bit buggy. So this is our first time doing this. This will be our worst one, and we'll only get better from here if this proves popular enough. And this may, Rigo said that this is the best one yet. So, and I hold to that. Once again, I'll let everybody introduce themselves, but real fast, my name is Diego Salazar. You guys have probably seen me before. I run Cypher Stack, and I found all these guys, and they are the best at what they do, and I said these guys got to be a part of my team, and now here they are. Let's go ahead and go down the list, starting with our research division lead.
Oh, is that me?
That's you.
I didn't know I had a title. I just thought I was that guy. Hi, everybody. I'm Dr. Brandon Goodell. I got my PhD from Clemson University in 2017. I worked for Monero Research Lab for a couple of years, doing sort of like freelance, sort of crowdsource your own salary sort of situation. Moved past that to Geometry Labs a couple of years ago, and then fast forward, and here I am with Cypher Stack. Been working on the Monero protocol off and on since 2014, and other protocols off and on, honestly, basically since then also. So we should probably go alphabetically, right? I'm Dr. Brandon Goodell, so I guess next
That's
up
me
is
next.
Salazar. Yeah, there we go.
Then I forgot my last name. My name is Rigo Salazar. I am Diego's younger brother. I have been into mathematics for my whole life, and so ever since Diego's been involved in the cryptography community, he's like, "Hey, would you be interested in this? Would you be interested in this?" And I was like, no. And then I learned that it involved a lot to do with prime numbers, and I was like, hold on, actually, maybe I am interested in this. I graduated with a master's in mathematics. And an undergraduate in civil engineering, but I don't really do that anymore. I have this as a part-time job, so I get to do math, which I prefer to do, and then I have a normal, a kind of more hands-on contracting job, which I do. So I kind of divide my time between the both of them.
All right, I guess that's me. Hi, everybody. I'm Dr. Freeman Slaughter. I got my PhD from Clemson something like 2 weeks from now. Give or take. We'll see when they send it in the mail. I am fresh off the boat back from Tokyo, and of course, I got COVID. So I will be COVID patient 0. I'll try and be more of like a fly on the wall for this one, except for when I unmute and say something stupid. But I also might have to leave early, depends on how I feel. Anyways, happy to be here. Wish you could be under better circumstances.
All right, I guess I'm save the best for last. Hi, I'm Luke Shermowski. I got one of my masters at Youngstown State University and the other one at Clemson, both in mathematics. Love doing lots of pure math. Been working here for like 6 months, 7 months at this point. Just doing crypto stuff. And yeah, that's pretty much it. Just doing lots and lots of math.
All right, thanks, guys. I our research meetings are generally pretty informal, and we're going to try to retain a fair amount of that in this live stream. So we're not changing ourselves too much just because we have other people watching. And you know, if this is popular enough and people like it, then we can do more of these. If nobody likes it and like this was the most boring thing I've ever watched, then
We're
we
still
don't
going
have
to meet
do
anyway.
That's right. We're still going to meet just outside of you guys' purview, and we'll be sad that nobody liked it, but that's the way it goes sometimes. Maybe we can have special guests sometimes, and you know, maybe we'll turn into a full-blown media empire.
Whoa.
That might be something that happens.
That
Probably
would be
not.
cool.
So in the interest of kind of pushing us along to the math stuff as soon as possible, we had slated to talk about Mimblewimble today, and that's, you know, kind of the general Mimblewimble, and we've been looking into kind of non-interactive transactions for Mimblewimble in the past, and Beam as well with their Lelantis Mimblewimble, which we probably will not be able to cover in depth today because we were doing a bunch of other stuff this week. But all these things are on the docket, not necessarily because we're doing work for any of these projects or endorse any of these projects, but because we want to know what's going on with the math stuff. We want to know what's going on with the privacy stuff, with scalability, with cryptocurrency. So we typically take time to discuss not just what we're working on in person, but also, you know, what are the latest stuff or things that we lack knowledge about. So today is going to be Mimblewimble. With that, I will shut up. Nobody's here to listen to me rant. You can go to that 5-hour podcast that Luke and I did a week ago with Vlad if you want to hear me talk and talk and talk. But I will go ahead and stop talking here and pass it off to Brandon, who's going to be talking with us about this.
Yay.
So like Diego said, we're kind of focusing a little bit on Mimblewimble today, but the way our research meetings oftentimes go, for the people who never observed one before, we usually have a couple of random questions to start. What I like to do for research meetings is we tend to go around the circle, describe what we've done over the past couple of weeks, describe what sort of accomplishments we've had, what we plan on doing the next week, and then start addressing specific questions that we've come up with. And that usually takes about half the meeting, and then eventually we get to this point where we tackle the topic of in question, which in this case would be Mimblewimble. However, I feel like since Freeman's been out of town for the past couple of weeks, and since I wouldn't say things have been in a lull at Cypher Stack, but in fact, quite the opposite. A couple of weeks ago, we came out with Silver Bullet, which was a tremendous amount of work.
Yeah.
And is still probably riddled with errors. So anybody out there who wants to just look for mistakes, then that's a good paper to start looking into. But because of that, we're kind of not necessarily like I said, not on a lull, but the last week or two, maybe not necessarily been the most productive in terms of research. We've been reading a lot. So rather than going around talking about what we've been getting done over the past couple of weeks and what sort of accomplishments we've had and what we plan on doing in the next week, let's just get directly into some questions. Are you guys okay with that?
Yeah.
Okay, cool. So from my understanding, Rigo, you had some questions about algebraic geometry and elliptic curves.
Let me pull it up, because let me look at, mostly when we're doing Project Snort and Sweet, as we're going over the stuff over and over and over again as we were making this project, making this whole paper, a lot of the stuff kind of like, okay, I accepted it, but I didn't like really internalize, like, oh, what is this? And last we had met, you had, I remember I had asked, because when we add that third dimension of Z, like, why is that one always the point at infinity, why is it 0, 1, 0? Why is the letter Y equal to 1? As opposed to Z, because like conceptually in my mind, I was like, well, if we're adding the third dimension, wouldn't it make sense to do that one? So that was helpful. Let me take a look.
So for the viewers, Rigo just mentioned Project Snort and Sweet. We at Cypher Stack like to use project code names for our projects, just because otherwise we're constantly referring to, oh, that one paper by so-and-so, or, oh, no, I don't mean that paper, I mean this paper by so-and-so. And it gets super, super confusing. And Freeman and I had, for this Silver Bullet idea, we had this like what seemed like a nice, short, sweet paper on our hands. So we called it Project Schnort and Sweet, or Project Schnort and Sweet. Unfortunately, it ended up being not short. So anyway, okay. So did you identify your question?
I think so. One thing that I kind of want to know a bit of a distinction of is the difference between projective points and k-rational projective points, where k is the field. Because I know one of them is dealing with like the closure and one of them is not dealing with the closure, but like what is kind of a bit of the difference? And if Brendan, you wanted to pull it up.
Yeah, so actually that's entirely the difference. So if I have a field K, and I'm defining an elliptic curve over that field K, not all of the points that... Okay, so a curve over a field is a polynomial, and it's in fact the set of the zeros of that polynomial. So if I want to know what are the zeros over a certain polynomial ring, then if I might get some answer, and it's a couple of points that if you plot them out might look like a curve. And actually they don't generally look like curves over finite fields, but if you plotted it out, you might imagine it as a curve.
Right.
But if that ring or that field doesn't have enough elements in it, then you have very, very, very few points on the curve, because the number of roots that solve the polynomial, there's far fewer of them that solve it over that base field, as opposed to some field extension, which is generally, you can think of like the algebraic closure of the field extension as containing all possible roots.
Okay.
So by starting at the field K and then lifting up to K bar, which is how we denote the field extension of the algebraic closure of K, we're throwing in all possible points that could possibly correspond to that polynomial. Now, what are the K rational points? It happens to be the ones that are in K already. So you can think of it like the real polynomials versus the complex polynomials. X squared plus 1 doesn't have any roots in the real numbers.
Right.
But it has plus or minus I as a square, as a root in the complex field. So by going from the reals to the complexes, you gain these additional roots. And if you plot them out, that's the difference between the k-rational points on the curve, which is only the ones from K, versus all the points on the curve, which are from the algebraic closure.
Okay. I'm going to sit and stew on that for a bit.
So yeah, the word rational comes from like the rational numbers. If you think about a solution to a polynomials over the reals, if it has rational solutions, a over b integer divided by integer, then you can rationalize those things and then turn them into like integer solutions, right? Using some, like Diophantine approach. So essentially what you're doing is you're restricting from the whole space of all possible roots, which might include things like the square root of -1, down to this space of fewer roots, but they all have to be rational in terms of like a over b, if that makes sense.
Okay. And Luke, were you about to say something or no?
Yeah, I was going to say, while you're stewing on that, there's been something that's been coming up in the reading, and I'm not sure, maybe it seems like something Brandon, you or Freeman would know, or maybe came across, but there was this, whenever you're talking about like isogenies and whatnot, the idea is that you have like an almost isomorphism. It's like the stuff that you aren't isomorphic on is like small, like finite or whatever. And the idea, bilinear pairings have been showing up in like 2 or 3 of the papers that I've seen. And me and Freeman talked about this because Freeman was like, don't waste too much time looking at it because it's really messy and kind of gross. But kind of like marrying the two together, is there any literature on like almost bilinear pairings, or does that kind of idea not really make sense?
Actually, yes, I did some research into almost bilinear pairings back in the day. There was a couple of really cool problems that I came across when studying for the Putnam, where they were almost like analytic in a sense. They were in that weird little intersection between analysis and algebra, where it was a bilinear pairing, but they were looking at it in terms of analytic ideas. So the idea is you have these two interesting spaces, and you have this almost bilinear pairing, where it's bilinear on like this really nice set, but then there's this awkward set. So then you use analysis ideas to try and bound its behavior on this awkward set, and then its behavior on the nice set is already bounded, in some sense. I haven't seen this utilized in cryptography generally because that bad set forms problems. So you'll get like some sort of decoding failure or something along those lines. But this is sort of the point with these isogenies is you don't really want them necessarily to be the nicest things in the world. You just want them to be mostly nice everywhere that you're going to come across them.
So on a related note, I wouldn't say identical, but do you guys know? Okay, so if I express an elliptic curve in the Weierstrass form, it's y squared minus x cubed minus ax minus b.
Yeah.
Right. You don't always have to express it that way, right? And in fact, the ED25519 curve, the way that DJ Bernstein avoided copyright problems, I think it was or patent problems back in the day, back when like crypto had a slightly different like approach in the copyright or patent world. He just rotated the whole thing, and he wrote it x squared minus y cubed minus ay minus. And so it occurs to me that like pretty much any rotation of the elliptic curve is still going to be an elliptic curve, right? And so and that's actually a really simple isogeny, right? Because all you're doing is you're rotating the thing. And I'm not even sure if I guess technically it would have to be an isogeny. So that's the first thing that popped into mind when you guys brought that, or when you brought up isogenies this morning, Luke, because it occurred to me this past weekend.
Wouldn't the rotation just be like a straight isomorphism, or is that not right?
Yeah, it should be.
Okay.
Well, actually, I'm not convinced of. It probably should be. I'm not necessarily convinced of that, because if you rotate it by an arbitrary slope, the slope is parameterized by the field elements. So I'm not sure if any rotation of that thing will always have the same number of elliptic curve group points. I'm not sure. I haven't thought about it long enough yet.
It's kind of
but hypothetically, you should be able to compose them.
Yeah.
Yeah.
So, like I rotate by this, I rotate by that. It's the same thing as rotating by that. So my heart says isomorphism, although my intuition could be wrong.
That sounds reasonable. Right, but not.
Oh well, I think it would have to be right because.
Well, I should be able to compose arbitrary rotations over the algebraic closure, but can I compose arbitrary rotations when the slopes are all field elements, like base field elements? I'm not sure. Again, but your statement about your heart telling you what's true versus, I'm with you on that. My heart tells me it's true also that it should just be isomorphism.
So, real quick as a comment, I gotta say I really like the idea of like an almost something, like the almost isomorphisms. So cool. Like,
almost norms. They're not called almost norms. They're not called pseudo norms. But there's like a bunch of structures that if you throw away the notion of most of the properties of norms, you can get to this like proto norm, and I don't think it has a formal name. And
norm in the context of linear algebra.
Norms in the context of linear algebra are special subcases of these weird generalized norms. But the thing is, dude, actually, since I'm talking to mathematicians, if you have any monoid, so do you guys know what a monoid is?
Yeah.
Okay, so a group is or monoid for the audience members. A monoid is a group that doesn't necessarily have all inverses. And so any monoid, you can impose a partial order on top of it that is induced by the monoid operation. So in an elliptic curve context, the operation is just elliptic curve group point addition. And since the whole group is cyclic, every element is related to every other element. So the partial order is like trivial. It's boring. But if you have a general monoid, you say A is related to C if there exists a B such that A plus B equals C, right? So this provides this big partial order structure, and it turns out that you can define some really, really general norm-like properties on all monoids from that, and you can draw crazy conclusions just from the monoid stuff. for example, in commutative ring theory, almost all ideal theoretic results can be just characterized in terms of the monoids and the norms of the monoid of the ideals.
That's cool.
And the norms imposed on those things. So in fact, you can throw out most of the ring theoretic characterization of things and prove most ideal theoretic stuff for rings without even touching ring theory.
Ooh, I like that a lot.
Yeah, it's kind of cool.
That's really satisfying.
I'm glad to hear that. Okay, so isomorphisms, norms. We talked a little bit about bilinear pairings and bilinear maps, and I actually have a question for Freeman, and actually I have a question for everybody. If you have a square matrix A over an appropriately defined field, and two vectors x and y with compatible dimensions over that same field, then X transpose AY is a bilinear map. But in lattice settings, nobody uses that bilinear map the way that we use bilinear pairings in elliptic curve group settings. So why?
I actually disagree with that.
In principle, if they did, then you could do a Diffie-Hellman style exchange, doing X transpose AY. Nobody does that.
Well, in the lattice setting, we take advantage of some, and it's been a while since I've done lattice. Luke might remember, but there's basically some nice decomposition. It's not lower upper, but it's something along those lines. Maybe like a householder type decomposition, where you turn A into like some BB transpose, something like that.
Right, a product.
Oh.
And then it has some really nice form, and then everything just kind of falls out nicely. Because then that looks like, it looks like a that as a bilinear pairing when X and Y are equal is just the norm, right? It's a matrix norm.
Right. Well,
so like X B transpose BX, that's just like the Frobenius norm.
Yeah, the norm with respect to the matrix A, or B.
Word.
So my question is this: why has so much effort been put into key exchange mechanisms like chems, like Kyber, if you can do a Diffie-Hellman exchange like that? I think
it's weak.
But go ahead.
I think it's weak to matrix methods. Like a Diffie-Hellman style exchange. I think that there's pretty readily you can just pull it apart using like closest squares or something.
So it's not that the bilinearity breaks down; it's that it's just easy to pull apart. Then you don't have that decisional property that we would hope for.
Yeah, and a lot of this bilinear pairing stuff, it was sort of like when we as a research group were looking at like elliptic curve stuff, is you have to be very careful. There's a lot of this bilinear stuff. There are a bunch of really nice results about bilinear pairings over the integers, and then a lot of really nice results about them over the rationals, and then a lot of really nice results about other fields or even rings. But those results, they all just say bilinear pairings. They don't really specify what space they're working over. So you see one result and you're like, wow, that's a really nice result. I should use that. And then you realize, oh, it's not over a finite field, it's over integers. So it's completely useless for you.
I think I remember looking at a paper and you were like, yeah, this doesn't work because it's over like complex space or whatever. Yeah. I'm like, oh yeah, I didn't even, very disappointing.
In fact, we ran into that problem with Silver Bullet because
I think was it a problem with the soundness that we were trying to resolve, and then it was a problem.
There was some result we were trying to rely on, but it wasn't true over finite. It was true over complex, which is very natural if you know anything about like the complex elliptic curve structure.
Yeah, but I don't recall what it was. Anyway. Okay.
So as an example, if I can, there's a really, really nice result called like Conway's 15, I think, something like that. There's a couple of other theorems like it, like the 1, 2, 3, 5, 7, 13. I'm just making up numbers, but it's sort of like that. The idea is if you have a bilinear pairing over like the integers, and you have non-trivial representations of this very small subset of numbers, then you can represent every integer. So that's really nice, right? It's like a completeness result. It says if you can satisfy these few conditions, then it works nicely everywhere. Well, that's a really nice result that we would love to extend to other spaces, but it's just true over the integers. So you have this nice result, you're like, wow, I'd love to apply this to my research. Nope, only applies in this one specific space.
So actually, this reminds me of where we ran into this with Silver Bullet. The Silver Bullet, we were like, all right, a divisor, according to the way that they were originally defined in the book, in those papers that we were studying, not necessarily originally defined like back in the 1800s, but the divisor is like a formal sum of these group points or symbols associated with these group points, and the coefficients on the sum are integers, and we weren't sure if those integers needed to be integers mod p or not, right? You remember that? So, and so like we were skeptical about whether certain results that were being taken for granted over the integers would hold over the finite field C mod PZ. And I remember that being a sticking point. And I'm to be perfectly honest, now that we're live streaming this, I'm not convinced we fully addressed that. But we'll see how that goes.
Okay, let me pause for a second. The theorem that I'm thinking of is the Conway 15 and 290 theorems. That states as if a positive integral quadratic form takes with integral matrix takes the values 1, 2, 3, 5, 6, 7, 10, 14, and 15, then it takes all positive integers as values.
Oh,
So
that's
you just-
so satisfying.
Just need to check this.
I'm
What
looking.
what are we googling, Freeman, or share your screen?
No, it's on my phone.
Here, I'll share it.
15 to 90.
The 15 and 290 theorems by Conway. A more precise version says that if a positive definite quadratic form with integral matrix takes the values 1, 2, 3, 5, 6, 7, 10, 14, or 15.
And 15.
And 15. Then it takes all positive integers as values.
So when they say like integral matrix, really they just mean like x, q, x transpose, where q is a symmetric matrix. So that's exactly what you were talking about earlier.
What does it mean by taking values?
So what it means is that you can plug in certain x values. When you plug it into that like x, q, x transpose, you get back 1. Take different values, you get back 2. Different values, ... up to 15. Then if you get that small subset, you can find values of that X matrix to give you any positive integer.
So you know what this reminds me of, even though it's completely disconnected? Going back to monoids from earlier. A numerical semigroup is a monoid that lacks the identity and can be injected into the natural numbers. So, for example, if you take the polynomial ring, but generated by x squared and x cubed, then the exponents that are allowed in that ring are all the natural numbers except 1. Because you can't write it, because x isn't in the ring and there's no way to rewrite it. Mm-hmm. So if you have a numerical semigroup, basically you throw out a small subset of a finite subset of the natural numbers, and then you take all the rest of the natural numbers and you generate the smallest semigroup that contains that thing. And so you always end up with a finite number of elements that are outside of that numerical semigroup. And there are certain theorems that I shouldn't say there are theorems that allow you to recover the whole natural number set again. But that's what this reminds me of. Is it's like, all right, well, if your generating set is too big, then you actually recover all of the natural numbers. But if your generating set is small enough, then you only capture all but a finite subset of the natural numbers, or something like that. Just a random connection that popped into my mind.
Freeman, are there extensions of this theorem? Because I see that it says it was proven uses Lagrange's 4-square theorem. So it seems like there'd be some real nice alternative results using similar number theoretic results.
Yeah, but you have to be careful. So the square theorems, you have like Lagrange, you have like the Fibonacci Brahmagupta, you have like Dickinson's identity, and so on. But then there's a theorem, I want to say it's by Cayley, I might be misremembering, But it basically says that the sum of n squares times the sum of n squares can be written as the sum of n squares only for very specific values. And those values are like 1, 2, 4, and 8. And then I think at 16 it fails. So if you look at these, it corresponds to the nice extensions, the reals, the complex, the quaternions, and the octonions. But then that's it. Everything else after that fails. So my heart tells me that yes, there are extensions, but there's only a few of them.
I could believe that. That's so nice, though.
These results at the intersection of number theory and like computer science are so weird, because you know that some data scientist or some database manager, somebody somewhere reduced a problem down to that, and then somebody, if Kaylee proved it. It's such a weird set of properties the natural numbers have.
Did you guys take a look at the 290 theorem? There was like a little extension where it's a finite set of primes to check to see if the matrix can represent all primes. That is an absurd result. Like the 2 through 73, you check all those primes and then you get all of them for free. That's so nice.
Oh, that's the next paragraph. You were one paragraph ahead of me. Man, you guys know the proof that every natural number is interesting. You know why?
Oh yeah. I went to a talk on that.
So it's an inductive proof. Let n be the smallest natural number that is not interesting. Then it's interesting by virtue of it not being interesting. So by induction, all natural numbers are interesting, because one is interesting. That I didn't do the base case. One is interesting because it's the multiplicative identity.
Ooh.
Okay.
All horses are the same color.
Okay.
So anyways, exactly this type of stuff I've thought about in the past, because he's talking about primes. Well, but those are primes over the natural numbers. You can talk about primes in other spaces, such as like, like on a Q would join minus D or something, or like the Gaussian primes.
Okay, so I'm not sure if are there any results talking about like, so this says it will represent all the primes. Does it talk about like what non-primes are excluded in these representations?
No.
Because that seems like that would be cool, because like if most of your integral solutions are prime, and there's just like, that seems like it would be a cool primality testing thing. But if it doesn't exist and it's like 50-50, then it's kind of useless.
Well, what you could do, and I've seen people do this before, is they talk about the density of representable solutions. So, like XQX, they talk about the density of those solutions compared to the open interval 0 to n, right? So then they let n go to infinity and they get that ratio. Well, if we're talking about the primes, the prime counting function has a very well-known density by Chebyshev or Erdős or whoever you pick.
15 different guys.
You could do some really interesting results by looking at the density of the numbers it does or does not represent compared to the prime counting function.
Yeah, I think that would be really interesting to take a look at, because that it's a relatively new result. That being said, it's still like 30 years old, but like new in the broader context of number theory. It would be neat to see if it's like, if the density of natural numbers which are not prime is 0, which probably isn't true. But if it's small enough, then you could come up with like a probabilistic prime checking thing. Because if your number does show up, well, it's probably prime.
I mean, I'll never shake a stick at a novel prime checking algorithm.
Yeah, I'm not sure how efficient it would be, but it is like matrix multiplication stuff, and that's pretty quick. So I'm going to take a look at that later.
And something else I'll point out is, this guy says that if you satisfy this small set of primes, then you satisfy all primes. Well, it also could be that for almost every integral matrix you care to check, if you represent all primes, you represent all natural numbers. So then, of course, you represent the subset of the primes. So there might be some something to be said about what's the difference there. Like, do you represent all primes but not all integers?
Well, that seems to be what it's saying, right? Because it would be kind of weird to phrase your result as we can represent all primes in this way when you have a result above where it's you can represent all numbers in this way. Like,
Before we
Well,
go-
what I mean is, let me clarify. What I mean is, his result says that we can represent all primes, but it might be true that for most of like random matrices that you care to check, they do actually represent all of them. But there's just a few solutions that only represent the primes. So then the theorem is only true for the primes.
Okay, so as we all know, prime numbers are a rabbit hole.
yeah.
We have some specific topics that we wanted to tackle today. So, of course, this is just me trying to get attention to myself because I'm playing Wimble. Guys, look at me. Okay, so what I'm going to do really quick is I'm going to exit the call and then rejoin so that I can use my document camera because I cannot easily switch videos or video sources right now in the middle of the call. So I'll be back in just one quick second.
Now we can talk about him behind his back.
Yeah. Wait, no, this is live streamed. You can watch the recording afterwards.
And then, because you guys were going on that, just to revisit it, can you re-explain kind of the initial premise of the 15 theorem? I found a video on YouTube. I'm a visual learner, so I'm going to watch that. But just so I have another summary at the beginning, what is the 15 theorem then? So if I have a positive definite matrix.
So the study of quadratic forms. The study of quadratic forms is a study of we have a vector x, we multiply it by some matrix q, and we multiply it by another vector, say y transpose.
Right.
So then when we multiply those in, then you get something out. You get some integer value.
Something like this.
So yeah, something like that. In this case, we're looking at x, q, x transpose, where q is either symmetric or positive definite. I think probably positive definite is the right thing to say here.
Right.
And then the question is, what do you get out of that from taking different vector values for x?
Okay.
And that's been a question that people have been thinking about for a long time because this is a very natural form. This type of thing pops up all the time in physics, pops up all the time in like numerical analysis. The question is, can we get a bead on what the output looks like from looking at the input?
Okay.
And
So pretty much depending on what the x vector is, you can kind of represent this x q x transpose like as of y. We can represent like all primes. We can represent all like numbers, essentially.
Well, the question is like, when can we do that?
Okay.
And that's what the 15 and 290 and then extensions to that say, is that if there are x values, or you can plug them in, you do this x, q, x transpose, and you get out numbers in some specific subset that's really small, then you can actually get everything. So this says you only need to check up to a certain point, up to a certain small point realistically, to know that exactly this quadratic form represents all natural number values.
Okay. All right, that is helpful, and I have a video which I will look at later.
By the way, this pops up a lot in dynamical systems and differential equations because when you have a differential equation, you normally want to linearize it, right? What would the next term be in like a Taylor expansion? It's the quadratic terms.
Yeah.
So normally, I don't want to say normally, but if we have like x dot equals ax and x is a vector like this, this is like the linearized form. The next term in Taylor style expansion would be like that. And then you do plus dot, dot, dot. And so we have a lot of good theory about how to handle linear systems of equations, right?
Yeah.
But actually expanding it out just to accomplish similar stuff using just those first terms, that's a big pain in the butt.
What would the cubic one look like?
I mean, it's just an integer matrix. Wait, what? What's the question?
What would the cubic look like when we're looking at the matrix? Because we had, I mean, I'm just
that I
looking
actually don't know.
at the,
I
what
would
the
guess
symbols
it's.
would be.
I mean, I would guess it's a tensor of some sort.
It'd have to be.
Oh.
Oh.
Yeah,
Maybe
let's
quite
do it.
bad.
But that's just a guess, and I should avoid that word around Luke.
Yeah,
Can you tell me what a
great.
tensor is?
I tell you, product.
I hardly know her.
Oh,
Um,
Brandon, real quick. Last question before Mimblewimble.
Yeah.
I wrote it down and then I
I'm
told
not
you.
in that much of a rush. Go ahead. Sorry.
So whenever we're talking about bilinear pairings, can we use like any bilinear map to induce a bilinear pairing, or is that not like?
So a bilinear pairing, and Freeman, please correct me on this because I'm going off the top of my head. A bilinear pairing is a map that goes from one group, or excuse me, the cross product of two groups to a third group. And it has to be bilinear in the sense that I think E of A, G, B, H. Gosh, I forget what the. Do you remember what the property is of bilinearity?
Yeah. So you're on the right track. Basically, you can like pull those two out.
Yeah, so it would be like AE. Yeah.
Yeah, and then of course you have like some other properties to make it behave nicely. But you have to be rather careful when you have these like
And this has to be a
bilinear.
one-way function, right?
Sorry.
Does this have to be a one-way function for it to be useful for crypto protocols?
I don't actually know. I'm not familiar with that.
Okay.
But you have to be kind of careful about what space you're talking about, because bilinear pairings as like a broad, like when we're not talking about just groups, we're trying to put these on like rings or like fields. A lot of times they end up just being trivial because this bilinear pairing condition is actually really rather strong. So if you're trying to find a bilinear pairing over like any like torsion-free group, it ends up being trivial, something like that.
Yeah, you mean that the E can't be the identity map.
And
by the way,
before we go jump into Mimblewimble, keep going.
yeah. By the way, when I pull this this A and B out, the way I wrote this is as if this group is a multiplicative module over the integers, like this. But actually, rather, excuse me, an additive module over the integers. But if you were thinking about it multiplicatively, you want E of GH exponentiated to AB, which is sort of this,
Yeah, that's actually what I was gonna say. Yeah.
Yeah. So that's just like a notational thing. I think I just got a bloop. Did I just get blooped?
No, that was me. I raised my hand because I was gonna say that.
Oh.
Another thing that I was gonna say is, if we're talking about like examples of bilinear pairings, there's like the while pairing, there's the tape pairing, and then I think that's pretty much it as far as generic constructions go.
That's my understanding also.
I saw something mentioned about like type 1, type 2, and type 3 pairings. Are those just different names for these, or?
It just depends on what your G1, G2, and G3 look like.
Okay.
So like you might want to ask, oh, okay, well, what examples do I have where it's G1 cross G1 into G1?
Yeah.
Right? That's like a very natural construction. And I think the answer is none.
I if I'm not mistaken, I think that's an open question.
Yeah, so you end up with these different types, which I really hate the notation for because it doesn't tell you anything about them. But some of these are nice in the sense that we have one construction. Some are nice in that we have two. Some are really bad and there's no known general construction.
The different types are these. Either G1 and G2 are the same group or not. So that's type 1 versus type 2 and type 3. Under type 2, there's a homomorphism between them, but they're not equal. Type 3 is they're not equal and not homomorphic.
Oh, that's a very interesting characterization.
Right? It's like 3 different depths of how unequal things can be. By the way, for the people watching this who like algebra, one of the fun things about algebra is generalizing the notion of equality. Your thing is not equal. Okay, well, maybe it's something slightly closer to equal, right? And then, your thing isn't quite that version of equal. Maybe it's another version of equal.
Almost.
Diego, you raised your hand. What's up?
Yeah, I have a question from the live stream chat. Why are they trying to change the number space, parentheses, if I'm understanding correctly, in parentheses?
What?
They're trying to change the number space.
Like change the space that we're working over.
We'll see if he responds.
How many people are
I'm
watching,
not
by the
sure
way?
what the questioner means about number space there.
Okay. Please expand, questioner, twig of the forest.
We're happy to answer the question.
Yeah, for sure.
How many people are watching, by the way, Diego?
We have 12 concurrent watchers right
Woo!
now.
Pretty
Yeah.
good.
Guys.
That's
We're gonna be rich.
That's
all the
almost
time.
3 times as many people as are participating.
30 people have checked in at one point or another and probably said, "Oh my goodness, I have no idea what's going on here." So,
My condolences.
But-
Well,
Classic.
Same.
yeah, so back to the idea. So can we can take this idea of a like bilinear operation and then like okay. We can jump in, we can talk about the bilinear stuff later.
Look, everything is a rabbit hole. The only reason I'm trying to get back to this is because Diego asked for us to talk about this specifically.
Yeah.
So, actually, I shouldn't say the only thing. It's also just interesting. So I've spent several hours now thinking about how to explain this, and I'm, excited.
Ready to
about
go. All right, let's do it.
We can get back to pairings after this. How's that?
Okay. Yeah.
Because honestly, pairings are so ubiquitous in terms of like applied protocols that we probably should have at least one meeting just on pairings. But at the same time, Freeman, can you make any comments about the quantum resistance of pairings-based crypto?
To the best of my knowledge, is not at all.
Because it's just all DL based, right? It's all
Yeah. Because so really, what you're trying to do is you're trying to extend the notion of Diffie-Hellman, and that was that point with the. If you could write it out again, maybe, or just like
I
go
see.
back.
Yeah.
You go back a page, Brandon. Yeah. So that like EAG BH, if you could point to it. Yeah, that one right there. You can sort of think of that's what you're trying to do with the Diffie-Hellman is I give you AG and you give me BH, and we both somehow figure out a way to compute AB and then some sort of operation on EGH.
Yeah.
Where we can think of if like G and H are the same and E is just the identity. I give you AG, you give me BG, and we both somehow compute ABG. So that's exactly the Diffie-Hellman exchange. This is trying to find a way to generalize that using these like bilinear pairings. But Diffie-Hellman is not post-quantum, and I don't think will ever be.
Well,
Asterisk?
it's not over
I
an
think the
elliptic
H would
curve.
be G in this case.
Yeah, you're right. Not over elliptic curves. Maybe like Ansel is post-quantum. I actually can't speak to that braid group stuff.
Yeah.
But there are constructions that are like trying to replicate this that are probably post-quantum.
Yeah, and Rigo, you said this should be a G, and if this was the Diffie-Hellman exchange, then I agree. This would be G, and that pairing would actually just be computing AG, BG equals ABG. And of course, computing that directly, given that as input and that as input without anything else is hard, unless you have a quantum computer. So representing it this way is kind of difficult because one of the things about pairings that's required is that we have to have an efficiently computable algorithm for it.
Okay.
And
Which is the hard part.
Yeah, expressing it this way as the DDH exchange or the DDH exchange this way doesn't quite work. What's up, Diego?
So Twig of the Force responded, basically just curious what the math is trying to be applied to solve.
Okay. So for like the bilinear pairings, I assume.
Let's go with that.
Probably.
So usually these pairings are for checking at the very end of a protocol whether or not some computations have been done correctly, essentially. So like if in a signature-based pairing or a pairings-based signature scheme, you have this check at the very end if this equals this or not. And then that determines whether or not your signature will end up being considered valid or whatever. Would you guys agree with that characterization?
Yeah, and I was going to say in a very generalized sense, different number systems, different groups had different rules and properties about them, which we can apply in different contexts to, like, for a new for different purposes. And that's a really general statement, so I'm gonna like break it down in terms of like a language thing. If there's hundreds of languages worldwide. There's English, Spanish, German, just a few off the top of my head, and each of them have their own uses and own unique words. So depending on the context that you're in, you would want to use a different language if you had access to all of them. If I were in Germany, I would probably want to use German. If I were in the US, I would probably want to use English. But context matters. So when we're trying to change the number system, like when we were talking about the divisors, talking about kind of like the affine space, the context is projective space. So what are we trying to work with? Are we using like the finite field of the integers? Are we using the integers mod p? It just depends. What are we trying to do? What properties of the numbers or group do we have access to, and which ones can we apply? So that's a more general kind of.
So let me let me follow up on Rigo's comment with an example, and then actually, Freeman, do you want to go first?
It's up to you.
Okay, so the example I was going to show is actually pretty simple. If you think about like algebra, if you wanted to compute a plus b squared, you would multiply these things out by foiling or whatever, and you get a squared plus 2ab plus b squared. And you're like, all right, everything's golden. Except what we did here applies for real numbers, complex numbers, any ring that we like, we can do this computation. But for some rings, 2 disappears. For example, if we look at the ring of elements 0 and 1, if all numbers are allowed to be 0 or 1, and we define 0 times 0 is 0, and 0 times 1 is 0, and 1 times 1 is 1, and 0 plus 0 is 0, and 0 plus 1 is 1. If we define these things, and we have a complete number system, we never end up leaving this number system.
Just scoot your paper up a bit, Brandon.
What? Yeah.
There we go. Perfect.
And we never like leave this number system. But in that case, 2 can be thought of as 1 plus 1. Where is 1 plus 1 in this list? It's actually not in here. If I do 1 plus 1, I'm going to end up with 0. Because these are the integers modulo 2. Integers mod 2, meaning that 2 becomes 0. So in this specific case, I have this, which is oftentimes called the freshman dream, because when you're in a calculus class, sometimes you'll be tempted to make that simplification just so that you can compute a derivative quickly or whatever. And of course, it's not correct. But so it's a dream statement. But it happens to be true in the integers modulo 2. And it also happens to be true in any ring with characteristic 2 or field with characteristic 2. So in this case, we have like typical algebra language, which is what Rigo was discussing. But we go to this region like Germany. And now we're in an integer modulo 2 land. 2 becomes 0, and this statement reduces to this statement. So oftentimes we'll have to like pick the modulus as part of our protocol design. But this is like just sort of like a real high-level overview of how ring theory works.
Yeah, I like that's a good analogy too. We go to Germany to make the math easier. Makes sense to me, man.
I'm not sure if Germans would agree with that statement.
Twig of the Forest gave thumbs up, so
sweet.
Cool.
Oh, yeah.
Okay. So, Freeman, what were you going to say?
I was going to talk a little bit about the bilingual.
Live streaming is on.
And we're back.
oh, not yet. I need to.
Yeah. That ruined a perfectly good yawn, Brandon. That was crazy.
Sorry.
Okay. I think it's put us back on. Let me just double check with the stream. Sorry, guys. I don't know what happened. It just said live streaming is off, and we were really sad.
All right, are we back? You think?
Okay, we're good. We're good.
And we're back.
All right. So Freeman, what were you going to say about language and mathematics?
Yeah, I was going to talk about the other bilinear pairing, the one on the top right, the XQY transpose. Just in case Twigga the Forest question was about that bilinear pairing. So in like numerical analysis, we have this problem where we have a bunch of lines, distinct lines in like an integer lattice, and the question is, out of the shape that they make, what's the minimum value or maximum value? So like in this case, the maximum would be up here. But it's a rather non-trivial problem just from looking at those lines, how to figure this out. So these types of numerical analysis techniques, which apply over integer lattice, they really change drastically if we're talking about like a lattice over the reals. Then we can talk about what happens over like a lattice in the complex, for instance. And then the problem is completely different. All those techniques which did apply suddenly don't. So this complex lattice now sort of looks like quantum stuff, and you need a completely new toolbox for it. So this rather highlights that even though we have the same form, the underlying space has a great effect on what we can and cannot do.
That's a great overview. Sometimes the way I like to think about this is like, if you're dealing with like the real or the complex numbers, or if you're dealing with the integers mod 2 or mod some other prime, it's sort of like the environment you're living in. So it's sort of like the atmosphere. And the things that happen inside of the atmosphere are determined by the properties of that atmosphere, right? But like what sort of animals can exist or what sort of plants can exist. And that's sort of like how I look at these things.
Oh, that's really good.
You've been watching too much Scavengers, Ryan.
Dude,
Yeah, okay.
so good.
So everyone here is given an analogy about language and math except me. So I feel like I have to.
Yes.
It's like different hairstyles. Luke.
Yeah. Okay. Well, the way I like to think about it is the alligator is always hungry, so he favors towards the bigger number.
That's a great addition.
There we
Dude.
go. We're done.
3 is less than 7 because the alligator wants to eat 7.
He's a hungry guy.
He's hungry.
Yeah. That's okay. That's all I got.
All right.
Oh,
So what does that mean about this? Anyway, okay. Let's talk about Mimblewimble.
Yeah.
And I'm not sure how far we're going to get into this before we're all like, all right, we've been talking for like 2 hours. How long has the stream itself been going, Diego? 'Cause
It says 2 hours and 30. Wait, the stream?
right.
Yeah.
But this conversation has been going on for 2.5 hours. How long?
Around an hour.
It hasn't. It's because I had this Jitsi open for a while, and that's the.
Oh, yeah, you're right. Okay. Sorry.
So we
Okay.
started about 11, a little later.
Yeah.
So like I was
Oh,
thinking
yeah.
about
So we're at an hour. That's no big deal. Okay. So Mimblewimble has an interesting story behind it, and I'll briefly explain it, and I'll also give you guys the lore of the community a little bit about it. But I want to emphasize that where I am making stuff up and or just repeating hearsay. Yeah, Freeman, what's up?
I was just going to offer that little bit of trivia as like a teaser, an intro to Mimblewimble.
Oh, okay. Go for it, because I was just about to say it.
No, you should say it then. If you have the lore, you should say it.
Okay, so Mimblewimble is
Can I
a
say
spell. Yeah, Mimblewimble is a spell in the first Harry Potter book.
It was a spell?
I believe so.
Well, what
Well,
would it do?
That was going to be my trivia. Is sure it's in Harry Potter. It's in the first Harry Potter book. Who's the first person to say it?
Oh.
Voldemort. It's the spell he used to kill
Cedric
Harry Potter.
Diggory.
It had to have been like McGonagall, right?
I will also accept the second person to say it.
That was mine.
This isn't something I looked up in advance. This is something I know because I'm an autistic nerd.
I mean, I would guess that Hermione is one of the two.
Ooh, good guess. Good guess. The first person to say it, everyone gets wrong because this is actually like really good trivia.
Arcus Filch.
The first person to say Mimblewimble is Vernon Dursley.
Dursley.
Oh.
Yeah. When Hagrid busts into the lighthouse, and Vernon Dursley, he's like searching for words. He says, and this is like a dead quote, something that sounds like Mimblewimble. Then J.K. Rowling thought that was actually like a good name for a spell, so she actually used it as a spell later.
Okay.
Is that this? And what does it do?
Then the second person to talk about it, if I recall, is Lockhart, where it's the tongue-tying curse.
Yeah.
Mimblewimble.
Oh, okay.
So, long story short, I'll just do this because why not? I don't want to inject personal politics into like a work cast, but I gotta say, like, I love the Harry Potter series, but not a big fan of certain people in the community. Okay, so Mimblewimble was, in terms of cryptocurrency, was dropped onto the internet pseudonymously under the name Tom Elvis Jetazor. I believe that it was dropped into a Bitcoin Talk group. And this is, of course, one of Voldemort's pseudonyms in the book. Or I shouldn't say pseudonyms, but it's an anagram of Voldemort.
That's cool.
And I believe that this was a character in the first novel also. Rather, like they were trying to unravel a mystery.
Elvis, whenever he fought Voldemort, he was like, I'm gonna take your wand, mama.
Blue suede shoes, etc. Now, who actually described the Mimblewimble protocol is up for debate. It's obviously like just a hearsay thing. But the first real formal description of Mimblewimble came from Andrew Polstra, which is the formal like GitHub. Like if you look on Google Scholar for Mimblewimble and you restrict your year, you can find it immediately. Because if you don't restrict your year, then you have like a lot of extraneous stuff. I'm gonna look it up really quick just so that we can. Just want to be real. I want to get like dates and stuff correct. Here we go. So October of 2016, Andrew Polstra uploaded a description of Mimblewimble to GitHub, which describes the whole thing. And the thing is that originally it was described on an IRC channel, not even Bitcoin Talk. So it was just like literally just. I mean, it was dropped as a document. But the way Mimblewimble works is real interesting. So you guys know how Peterson commitments work, right?
Mm-hmm.
So for the community members who are watching, a Peterson commitment C can be written as some amount G times a base point G plus some blinder times another base point H. So this is an amount. By the way, I'm probably getting things backwards, and Kayaba always gets on me about this because I use the different notation than everybody else. It's just because I have ADHD and I'm dyslexic. So these two things are elliptic curve group points that are publicly determined for some protocol. C is going to be an elliptic curve group point that is like representing your commitment. Your amount A usually comes from some small set, like 0 to the 2 to the 64th, or something like that. And this blinder comes from a cryptographically large set, like 0 to the 255 or something like that.
It should be chosen at random. And
it should be sampled randomly. And it needs to be sampled randomly every single time. These are one-time commitments. If you reuse the same opening data, by the way, the A-B pair is called your opener. If you reuse that data, then your commitment is obviously going to be the same point C. And if it's been opened publicly by revealing A and B, then you can't reuse C, which is why we need the blinder to be selected from a cryptographically large set, so that even if humanity uses this over and over and over again over the next 1,000 years, we're not going to come close to dipping into the total number of blinders that are available. Although hashtag, there's a comment that I went to back in 2019, Bitcoin Stanford, I believe, or 2018. I went to one of those two conferences. Actually, I think I went to both of them. But at one of those conferences, there was somebody talking from Amazon's key management system about how many Oracle queries they make each year. And they're like, we're already so much closer to 2 to the 128 than we thought we would be. Like, obviously 2 to the 128 is supposed to be a cryptographically large number, but like Amazon's already making something like 2 to the 40th queries each day. So yeah, so like, or rather, it might have been like 2 to the 37 or something like that, but it's just a couple of years ago, and like, it's obviously only gone up. So it may be that we need to use 256-bit or 512-bit as like a good baseline going forward in the future. But this is how a Peterson commitment works. And it's called a commitment because you can think of it as a secret box that contains your number. And it has a lock on it. I'm going to draw a box with a lock. The lock is your blinder B, and the box has your amount A in it. So if you open your box, then what you're doing is you're revealing your A and your B, and that opens your box. And so by revealing the box and the lock together, I'm revealing this public thing that perfectly hides my number, because I can pick any blinder, so any possible amount is possible. But opening the box to see what's inside is difficult. And opening the box to some other value A is also difficult. Now, commitments have some interesting properties. There's one of them is called hiding, and one of them is called binding. And they're about as evocatively named as you can imagine. A hiding scheme is one there where you can't see what A is, and a binding scheme is that you can't change A by opening it to a different A, opening your box to a different A. So the way Mimblewimble works is it notices that if a coin is a Peterson commitment, then you don't need to sign anything in order to spend it. You just need to open it. If you could open the commitment, that's equivalent to proving that you must know the contents. There's no further authentication necessary. So Mimblewimble's whole core structure comes from coins are Peterson commitments, and to spend them, you open them. Now, here's the problem. A transaction is some inputs and some outputs. It's also like a fee and possibly some additional data like an authorization or an authentication. Okay, so this is what a transaction is. Inputs, outputs, a fee, and an authentication. And if your authentication is built into by just opening the commitments, then you don't need signatures or anything fancy. Yeah. But the problem is this. How do you know if this transaction balances? How do we know that in Monero, for example?
Take the difference.
Yeah, you take the difference of the inputs and the outputs, and you show that you know that the difference must be zero. Or equivalently, so show the amounts in the inputs equals the amounts in the output plus the fee. Okay? This is what it means for a transaction to be balanced. Okay? Now, in Mimblewimble, what that means, if you can rearrange this thing, if the amounts are commitments to coins, these are like nicely homomorphic. Since this is a group element, I can add them together, right? I use additive group notation. A lot of cryptographers use multiplicative group notation, but because we're adding amounts, I like to think of these things as additive. So if I subtract these two sides from each other, that's the same as saying amounts in I minus the amounts in O minus F equals 0. And if you have a commitment to 0, that's equivalent to, if A equals 0, do that. If A equals 0, then C is BH. Do you guys see that?
Yeah.
So this is just a regular old public key. So if A equals 0, you can compute a normal Schnorr signature
Okay.
with this commitment C as your public key. So if your difference of your amounts is 0, then in principle, you should be able to compute a Schnorr signature on the difference, the difference in the commitments. Okay. So to write that down.
So in this case, the A is just this transaction kind of summation, and
So
you're
up here, A is an amount in a coin.
Mhm.
Here, each input and each output has a different amount. But
Right.
the whole transaction has to have an amount which is 0 in order for it to be balanced.
Right. Okay. All right. So you keep going.
Okay. So to write this down, in Mimblewimble, to show that we can spend C1, C2, Cn to create C1 prime, C2 prime, Cm, you make a signature with public key C1 plus da 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 plus Cn minus C1 prime minus da 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 minus Cm prime minus the fee times your base point. Now, ultimately, the issue is this. You've received these coins, C1 through Cn. You are trying to spend them to create these coins. If you're trying to send me these coins, I need to be able to know the opening data of these coins in order to spend them. So how do you create a transaction? Constructing a signature on the difference of the commitments. If the spender knows these and the recipient knows these. And the answer is Mimblewimble has interactive transactions. Where if I want to send something to you, you and I have to collaborate to construct a signature so that you pick the blinding data for your coins that you receive from that transaction.
Okay.
And then we collaborate to construct a signature. And then later on, in order to spend those coins, you have to interact with your next recipient.
So then, is there not a way to like fiat Shamir transform this?
And voila, welcome to... Okay, now, the short answer is yes. But, so this is like the opposite of like improv comedy where you say yes and. Actually, yes and. Okay, I'm going to change that to the difference between two sums. It doesn't really change anything, but one of the value, before I answer your question, Rigo, the value of doing it this way is that if you have transactions chained together that are, let's say Rigo, you and I are business people. We each run our own business. I buy things from you, and then you pay my company for services, and we go back and forth this way. And they're not necessarily related. Like, for example, I may be running a janitor service, and you may be running a bleach store. I buy my bleach from you, and you hire my janitors. And it's not that we have a direct relationship between those things, but we have this regular interaction back and forth where we trade cash back and forth, right? When you do that with Mimblewimble, if I have transaction 1 looks like this, and then in the next transaction, you spend these things.
So now I have all the primes.
And create new ones. Somebody just went, like they figured
Yeah.
out what's about to happen.
I already see.
Then you get this telescoping thing where that cancels with that. So this is called cut through in Mimblewimble. And the thing is, this can make it so that after many sequential transactions in between two people, you can collapse those things down via telescoping. Andrew Polstra calls it syncing signatures.
Sinking?
Syncing.
As in like SYNCH?
Syncing. Like you're
Like a
syncing.
boat.
As opposed to the opposite of a sword. Because what you do is kind of like he just defines a signature as having a height. And then if you have a signature of a given height, or two signatures of two different heights, you can reduce them to a single signature of the lower height.
Mm-hmm.
So he
That makes
called it
sense.
syncing, which sort of makes sense. Yeah, what's up, Diego?
So I just want to kind of give a real world look. I know you guys are in the weeds in the math and you're understanding the math, but I would like to give a very quick real world look about what this looks like. So Grin, not the telescoping, but the interactivity, because that's going to become a big thing here in just a little bit. Grin, Epic Cash, and several Mimblewimble Coin, Stack Wallet, which we make and whose channel is hosting this live stream. Stack Wallet has worked with Epic Cash, which is Mimblewimble based, and it was one of the first coins in Stack Wallet. And one of our big frustrations and issues is this interactivity, because with regular Bitcoin transactions, you give me an address, I send to that address. Like that's the only interactivity that we have. You give me an address as a receiver, right? As a sender, I send it to you, and you don't have to do anything. It's sitting there for you, even if you're not online, even if your mobile wallet is not connected or your desktop wallet is not connected. It's now just sitting there on the blockchain for you, right? You don't have to do anything. The only thing you do is when you want to spend it or see that it's there, you open up your wallet and it scans the chain and says, "Oh, there it is. Okay, that's there. It's yours," right? Epic Cash, Grin, Mimblewimble Coin, any other coin that's based off Mimblewimble does not work this way.
Mm-hmm.
How it works in practice is I, the sender, say, like, there's no addresses, right? I, the sender, say, I want to send 5 Epic or whatever, and then I generate a long alphanumeric string that they call a slate, a very long alphanumeric string, and I give that to you somehow, email, text message, whatever the case may be. You take that alphanumeric string, open up your wallet as the receiver, paste that in there, and press a button, and behind the scenes it does all the math and the signing and the whatever, and you generate your own alphanumeric string that you then send back to me via email, text message, whatever. I take that one that you, the receiver, gave to me, the sender, do one last thing of computations on it, and that's what I upload to the miners. So this is the interactivity. We have to interact with each other to make this happen. And if at any point one of us goes on offline, one of us is not reachable, one of us is not available, the process halts until such time that that person becomes available again, if that makes sense. So in Bitcoin, a transaction is literally just, okay, here's my address. Then you as the receiver, you go do your own thing. You can't go do your own thing, or you can, but that just means that the transaction will take forever to actually complete, because I need you to do your part to get me to my part. And if I'm offline, then, yada, yada, yada. Yes, Brandon.
Yeah, so a couple of points to add to what you just said, because everything you just said is totally correct, obviously. Essentially, Mimblewimble replaces addresses with pre-computed blinders of commitments. So I share a whole bunch of pre-computed blinders and then with you, and then you can create these outputs without actually interacting with me. And that way, there's no addresses, but addresses in Bitcoin and other similar currencies, those are nice because you post them once, they're one-time posting, but they can be reused multiple times. And so that's sort of like the trade-off. And I just wanted to throw in the notion that big alphanumeric string that Diego just described is just a whole bunch of the pre-computed blinders for use in that transaction.
So when the pre-computed blinders are sent over, are they sent over via Diffie-Hellman, or are they just sent over plain text?
I don't
No, it's called out of band, which means that there's no central server, there's no anything. Like I have to send it to you somehow. Like literally, I send you a text message with this.
Yeah,
Right?
so out of band meaning like off network. However, by side channel you want to get me those pre-computed blinders, then I'll be able to construct a transaction to you.
I'll send it to
So
you on a
actually, that's
Discord message or anything like that. At which point you have to literally copy paste from wherever I sent you, put it into go to your app, whichever one it is, right? Paste that slate in there, and do your own stuff to send back to me.
Okay, so I have a question. A key exchange, or excuse me, a key encapsulation mechanism like Kyber, the entire purpose of that is so that two people can come to an agreement about a short seed, like a 32, 64, 256 bits, let's say 256 bit seed. I think Kyber does 32 bytes, which is 256 bits. And so, and then from that, you use Shake, which is an extendable output function, in order to extract as many random bits as you like. And you can shake these like indices in a sequential order so that the two people have an agreement about what comes out of that shake. Shake is basically a hash function with an arbitrary output size. So why do Grin and Beam and why do they do it with the do it however you like approach? I mean, I suppose that you could just always have a unique wallet that does it its own way, and then only other people who use that wallet will be able to interact.
Correct. Yes. So, there are ways to do this to make it as non-interactive as possible and make it similar to Bitcoin. For example, if you run a server that is just always online, then you can make this process fairly instantaneous because you are quote unquote always online, right? If you're in person, you can scan via QR codes, right? Instead of doing copy pasting, and you can just kind of scan each other's QR codes. The goal is true non-interactivity. That would be the absolute best thing you can possibly get. We approach that. So what we did in Stack Wallet is Grin made an idea called Grinbox, which we work with Epic Cash, and so they kind of forked the idea and named it Epic Box, and it's this third-party, always online server that it's basically kind of like an email server in the sense that it assigns everyone who interacts with it an address, kind of like a Bitcoin address, and when you want to send, if I want to send to Freeman, and we can do this in Stack Wallet, after the meeting or in person, so we can kind of see how it works. It really starts to look like Bitcoin stuff. Because you give me an address and I send to that address. What's really happening is it's sending the blinder stuff that Brandon is talking about to that server, waiting for you to check in and pick that up and automatically do your signing and send it back to the server. So it's kind of like a whole it's holding the message for you, if that makes sense. It's holding the message for you. And if both parties are online at the same time, it happens fairly instantaneously. And I know, you guys are math people, and like this is kind of going into the computer science and how do we solve this with engineering type thing. So it might be, once again, when we're in person, I can show you guys how that looks and how that works. But that does add an element of third party. You're adding trust, right? Because that third party now kind of has a record. Not necessarily, because it could be all encrypted, so not necessarily of knowing how much is sent and stuff, but at least who's connecting to it from an IP address level, what time that occurs, right? So they can start doing some potential timing attacks and stuff. So there are ways that people are trying to make this non-interactive, because the interactivity is a pain. People mess it up. From a UX perspective, you send something you don't mean to send. There is one benefit. Like, I hate everything about this. This has been a huge thorn in my side. From a Stack Wallet getting this to work perspective, it's the absolute worst. The one benefit is that people can't send money to you as a receiver that you don't want. So like, let's say, in Soviet Russia, they want to send you dirty Bitcoins so that way they can claim, look, you're a part of this drug ring, right? And you had no choice to accept the money because the money just arrives. That's how Bitcoin works. If they know what your address is, you can't say, well, that's not mine. Like, well, look, it's in your wallet. With the interactivity from a receiver perspective, you could just not do your signature portion and send it back. And so you effectively don't accept the transaction. If you're using one of the things like Epic Box or Grinbox to eliminate that interactivity, then you can't really do that. But anyway, two people want to speak. Brandon, then Rigo.
Well,
Let's do Rigo first.
Okay.
okay. My question is going specifically to the telescoping aspect. In mathematics, when we're dealing with telescoping series, there's usually a beginning point and there's an end point, in which case then we have our final product. In a transaction history context, if I, as Brandon was saying, if I'm a distributor and he's a janitorial service and we're just going back and forth, there's not really an end point per se, because there will be another transaction until our business relationship is terminated. So with that being said, at what point...
Luke, can you go ahead and mute yourself? I think we're getting background noise from you.
So at what point is
Sorry, Rigo. Because of that background noise, I was very distracted. Can you start over? Sorry.
Yeah. So in a mathematics context, like when we're in Calculus 2, we're dealing with series. And we're talking about telescoping series. There's usually a beginning point and there's an end point.
Yes.
And then we have the final product. In a transaction history context, where I am the distributor of chemicals and you are the janitorial service and we're interacting regularly, there is not really an end point with a neat little bow. Because you and I continue to do more and more transactions. Therefore, at what point do we kind of cap this off? Okay, this batch of transactions is what we are.
Right. So the short answer to that is whenever you want. So in practice, for example, banks might want you to, let's say, close. Okay. So a similar question happens when you're talking about payment channels, because you and I can open a payment channel and we can trade transactions back and forth. And then eventually we have to finalize that by closing back onto the blockchain. Mm-hmm. So that might happen monthly. That might happen weekly. That might happen on a fiscal quarterly basis. That depends on how the participants want to do it. But the idea is to go for long enough that you have some efficiency gains in terms of things actually finally hitting the ledger. And the reason that this is weird to me is because, in my opinion, and this is going to be, this is a hot take, so you guys can take this for whatever you like. In my opinion, Mimblewimble's cut through is a bad thing. Because the point of a ledger is to record all transactions.
Right.
In my opinion. If you want to do this, then that's fine. This is like an off-chain sort of thing. And then eventually finalizing it onto the chain, just the inputs and the outputs are the important thing. So that's really great. But if you want a record of these interior transactions, and that's why you're using a blockchain, is so that you have a nice public record, then Mimblewimble's cut through is actually not a helpful thing. After all, you have no record that these transactions ever occurred on the blockchain. So in my opinion, that's questionably a benefit. There are certainly use cases where that's nice, don't get me wrong. But I'm not necessarily sure if that's what ledgers are really for.
There. And then I'll raise
Diego raised his hand.
I think Freeman was first.
But Rigo, before we move on, did that answer your question?
That did answer the question and opened more questions.
Okay. Cool.
But so Freeman should go first.
Okay, Freeman, what's up?
So I had a question about these fees. I understand this telescoping perfectly, but then at the end we'll have the sum of all these different fees. That seems to me to not be ideal, because if the record just has the first and the last, ideally we would just want one fee attached.
Yep. And so the cut through is partial. So when I said a minute ago that you have no record whatsoever on the blockchain that these interior transactions occurred, actually, come to think of it, the fee is what you pay to the miner.
Right.
And so each of these interior transactions, I suppose you don't need to take the fee into account, and you only need to handle the fee at the last transaction. And that one fee would cover the whole chain of interactions.
That would
Well,
make
yeah,
sense.
but wouldn't the fee still reveal like how many cut-throughs there were?
No, because you only need to pay fees for the transactions that enter blocks. You're
Okay.
paying a fee based on the data that you're storing on the blockchain. All these cut-through things never end up on the blockchain.
Oh, all right.
sense.
Okay, that's interesting.
This would look like Alice sending this, Bob receiving this, and then both agreeing to pay this fee. The fact that behind the scenes everybody did these backs and forths, and they agreed on the fee at the very end, that's up to everybody else. So that's another nice thing about Mimblewimble is the out of band stuff that you make assumptions about. It's like, well, that's not really the business of the blockchain. So like I have controversial takes on Mimblewimble. Okay, Diego, what's up?
Yeah. So what you just said about the blockchain being a record, this has pros and cons absolutely, because it means that the chain can be quite small, and because of that, there was a big scare not quite some time ago in the blockchain space about how are we going to scale, and it is an outstanding question today, right? Because the blockchain just gets bigger and bigger and bigger, and it never gets smaller. So when we're talking about scaling, what's the throughput, how many transactions per second can we do, what is the storage like on a blockchain for somebody that wants to run a full node, and what is the bandwidth in terms of downloading an entire blockchain if you want to start a full node and you're syncing from zero, right? So Mimblewimble was kind of proposed as a way with the cut through to keep that blockchain, like, it's still going to grow, right? But it's going to now grow at a smaller pace than the other stuff because of this telescoping. But in practice, right, having worked with Epic Cash, we got a ton of support requests from people who are wondering where their history is, right? If you are syncing from scratch, let me put it like this. I have used Epic Cash in the past. I've made transactions, and as long as it's still on my mobile phone, all of that stuff is saved locally. I can see where it is sent, when was sent, when was received, just like other Bitcoin stuff. Not because that stuff is on the blockchain, but because my mobile phone is locally saving that data. But if I sync that same seed on a different phone, I don't have any of that because none of that is on the blockchain. The only thing I end up with is the output. So I just see how much money I have, but not when it was sent, what was received, and when. So a lot of people, and again, I'll show this to you guys in person when we get all together for Stack Attack, and I'll show you what this looks like. It's very frustrating for people because that whole record of, this was when I sent, or trying to prove that you sent a transaction during this time or whatever, like all of that is gone if you have to switch mobile phones, if you have to sync from scratch for any reason. The only thing you have is the outputs and how much you have right now. And
I have to take the call. So Luke, I was first, but I'll let you go first.
So that is it sounds fine. Like, you talk to any blockchain person, like, maybe that's probably fine. Like, the only thing that matters is how much money you have. But no, like, there's, even in the regular fiat world, we go through our bank statements to see, oh, this was when I paid Amazon, or this was when I paid this person, or whatever. Or if you have to prove to the government for tax purposes, this was when I bought this. It's actually a bigger deal than people think that it is. And it is, to this day, one of the primary frustrations that a lot of people have with Mimblewimble based coins. So telescoping, reducing scaling in that sense is desirable sometimes, but it adds a lot of problems you wouldn't think. It does add privacy in a way, because a lot of those transactions are now no longer on the chain to be looked at, right? What went where and when. So it does add an element of privacy, which is the primary reason why we're looking into Mimblewimble, actually, because it does have some privacy preserving properties, but they're not strong ones, because the miners are the ones that perform that cut through. And that means that the miner can just on the side keep an entire transaction graph pre-cut through there, because they had the information of, okay, this is what I do need to cut. They have that information. So they could just kind of on the side in their own whiteboards or on their computers just keep track. This is what I cut through, right? This is what I cut out. And I'm just going to keep that here. And then you can potentially like sell that.
And then of course you have like robustness issues with that approach, which is the same reason that like payment channels are kind of crappy in the first place. And rather, when they're crappy because local storage goes out the window. Some cosmic ray hits your hard drive and wipes your local history of all those chains of transactions. And then all of a sudden, neither party has a copy of it for some reason. And then like, it's just a cluster.
Last thing for me, then we'll go to the questions. The way that Stack Wallet is trying to solve this is we have in our Stack Wallet called Stack Wallet Backup that it backs up all your seeds, all your things, because, you know, we support a lot of cryptocurrency. So this is just supposed to be a way that you can very easily, very quickly get all of your wallets moved from one phone to another, that kind of thing. And in there, we try to keep all of the history that you have on your Mimblewimble-based coins. But that is obviously very specific to Stack Wallet, like Brandon alluded to earlier. If other people were to adopt the Stack Wallet backup standard, then they would be able to import our stuff, which is all open source. You know, it's not proprietary. They could add that stuff to their wallet, so people could back up their or get their stuff there in another wallet as well. But right now, only Stack Wallet uses Stack Wallet backup, so you're really limited going Stack Wallet to Stack Wallet. So it's a bit of a bummer. Anyway, sorry. More questions from
no problem. No. I mean, like, look, you have your elbows into the guts of this stuff in a practical, applied sense, and so your experience and expertise here is extremely welcome. I didn't realize that you had so much practical experience specifically with Mimblewimble. It's cool. Luke, you have a question or thought? You are muted, my friend. Yeah. Oh wait, no, you're not muted, but I can't hear you.
Muted on Jitsi. In order to solve the background noise, you may have swapped an input or something.
Diego, you should call the Stack Wallet backup just Back Wallet.
This is why you're not on the marketing committee.
As Luke is trying to get that solved.
So let me just summarize really quick some of the thoughts that I have written down here. The scaling and throughput stuff about Mimblewimble, those are some interesting properties. There seems to be some trade-offs. Storage requirements, local storage requirements. If you have a protocol that is going to, by the way, Luke, if you do get that solved, start waving your hands and all. Yeah. Okay. If you have a protocol that is intended to be run on lightweight devices, then Mimblewimble is going to be preferable, and or at least Mimblewimble-like techniques are going to be preferable. But that leads to, Luke is ready. Yay.
Okay, can you guys hear me now?
Yes.
Yes.
Okay,
No
wonderful. No buzz. Okay, sorry, that was my air conditioning. So if I start sweating, you'll see.
Luke's nervous.
Yeah. Okay. So actually, I have a handful of questions, but I'll start with the first one. And I think this is more targeted towards you, Diego. How does the Mimblewimble stuff work with like government regulations? Because it feels like this cut through thing is like
it's more like
hugely yeah, exactly. This feels like you have to like. I'm literally handing someone a dollar bill and they're accepting a dollar bill.
I can say something about that, which is that according to the IRS, every cryptocurrency transaction is a taxable transaction, with only certain exceptions. And so every single one of those interior transactions are technically taxable transactions. Now, having said that, if I have you paint my barn in exchange for a few chickens, that is a taxable transaction. And both of us are, in fact, required by the IRS to report that sort of thing and estimate the value that both of us lost in exchange during that transaction. And that is not a practical thing that most people worry about. And the IRS is like practically it's a practically unenforceable rule. So in terms of comparing it to like everyday things that already exist, it's comparably like unenforceable in terms of like it being used for things like that. But because it's a cryptocurrency, you can be transferring arbitrarily large values, and then that never has a record. What's up, Diego?
So my 30-second response to this is it really depends on the country that you're in. One of the things that the Mimblewimble people try to say is like, hey, GDPR or whatever that is in Europe, right? This works with that because people, like blockchain doesn't work with that because you can't get rid of a record when asked, right? And that's kind of the whole European thing that you need to be able to ask a business or whatever, can you please get rid of these records? And they need to be able to do so. You can't do that with typical blockchain. So one of the slants that Mimblewimble type people were going on is like, hey, you know, this is GDPR compliant because things get cut out, which you don't necessarily get to choose what gets cut out. So it's not 100%. It's a bit silly. But yeah, you know, in the sense that now you can't prove certain transactions or whatever, only that you have this money and you can't necessarily prove where it came from. All of this is an open question. There is no precedent from a court perspective in any country that I'm aware of about this. So yeah, if it raises an eyebrow, it probably should. And there's not a lot of there's zero precedent to really answer this question beyond speculation of what you think some countries would rule based on similar type cases in the past.
Okay, and then my follow-up question is, you said that this miner could keep like a record of the transactions back and forth and stuff, and then potentially sell it. But is that even like necessarily a valuable thing? Because couldn't I, if I was a miner and I'm getting paid based off of like the transcript that I'm selling someone of these transactions, couldn't I just like artificially like add to the end of it?
Sure, maybe. I would like to posit in a world, you know, I'm an author. I want to posit a world that doesn't exist where Mimblewimble really caught on, and the people were touting its privacy properties everywhere and saying like, you know, and Mimblewimble helps you stay private. It would then behoove the powers that be government system or to run their own miners, so that way they have their own transaction graph because they do want to know where money is flowing, or for a miner to be able to say, hey, look, hey, Amazon, the whole world has adopted Mimblewimble, and I know that you guys want to know what people are spending their money on, and I've got a transaction graph with reasonable assumptions about what this money is going to. I'd be willing to sell this to you for, you know, X amount of money. I mean, if you become a miner right now, you have no idea about all the cut through that happens from Epic in the past. You would have an idea from now going forward, right? Because it's up to you to do that cut through. So anyone who has kind of an older, who's been mining for a longer time is going to have a more complete picture about where all this stuff is going. It's potentially valuable information that is toxic to people's privacy. Even though it's not getting saved on chain, you can still purchase that information from a third-party market type thing.
Right. Well, it just seems like it would be an incentive for someone that's selling large amounts of data to pad the data by making a bunch of like false back and forths, because the back and forths aren't recorded anyway. So couldn't I just pretend to have a bunch of transactions like with myself and then just add that to the transcript?
Oh, I see what you're saying. So what you're saying is like, if I present a pruned blockchain, then I guess step backward to claim what the blockchain was before pruning.
Mm-hmm.
Yeah, because I lost information. There's no way for me to verifiably reconstruct that.
Right, and the only way to make this somewhat accurate is to potentially purchase from 3 or 4 different people, because then you compare the chains to each other and say, oh, like this guy added a whole bunch of stuff that these other people don't have. So
which reduces us back to the entire idea behind decentralized ledgers in the first place,
right?
Which Satoshi solved with hash chains, right? Like,
right. That literally comes full circle, because that's like what, remember when we were talking about proof of stake and how proof of stake people can propose a whole bunch of alternative chains, and it introduces weak subjectivity. It's the same thing here, right? Where potentially you have 4 or 5 different people, or way more, keeping track of the chain state, the actual pre-pruned, pre-cut through chain state. So yeah, it's very silly. But yeah, we got to go to Luke, then we got to go to Rigo, then we got to go to Brandon.
Yeah. Well, I guess just to sort of finish it off, it just doesn't seem like if I were to buy. Okay, so if Rigo, Freeman, and Brandon are all selling me what they're claiming is an accurate transaction snapshot, and they're all different, then there's no way to know which one is the correct one. You need some sort of majority rules consensus.
And that actually brings me to my next point. But so let's pause on that thought for a minute. Because another thing that I want to bring up before I'm sorry, I got to jump in because there's this implication that, so remember, we started this conversation, we hit interactivity, we were like, oh, I wonder if we can fiat Shamir that. And then we went into cut through and then started talking about that because it's really interesting. But the reason that those two things are linked is because Fuchsbauer wrote a paper called Non-Interactive Mimblewimble Transactions Revisited, where he proposes a way to make Mimblewimble transactions non-interactive, and he uses Monero-style view and spend key structures to do it. However, the cost is cut through. So there seems to be some sort of trade-off between the existence of cut through and interactivity when all you're doing is opening commitments to spend coins. So I'm going to write that down. There seems to be a trade-off between interactivity,
cut through, interactivity,
and cut through. Now, like we already said, we're not convinced that cut through is a universally good idea, right? So, having said that, that's why I wanted to jump in, is because there's actually like a punchline lurking here. Okay, here you go. Now,
so this is a continuation of my original question, and it's kind of connected to a little bit of what Luke was saying as well. So going along with the analogy of where I'm a distributor and Brandon was a janitorial service. Say Freeman runs like the electrical company, which like supplies the power to my warehouse or whatever.
Sure.
And so, but I also have solar. And so like there's an interaction between him and myself as well. So I recognize that, Brandon, you and I can have our own telescoping relationship with the cut through. And then I also have a relationship with Freeman, this telescoping relationship, and then cut through. It appears to me, at least at face value, that, because you had said the cut through can happen at any point, like when we stop this series. But if I'm interacting with multiple parties within like a few days, like, so I'm interacting with Brandon, like say 2 or 3 times in a span of 2 days, then all of a sudden I have to pay Freeman. It feels like I am forced into ending the telescoping series, so that way my money is like consolidated, and then I can interact with Freeman.
So
but then that makes...
Yeah, I see where you're going with this. The way I like to think about this is payment channels. So instead of me and you just broadcasting transactions across the whole network for everybody to see, you and I, like, this is Alice, Bob, Charlene, right? They're connected in three distinct payment channels. And each payment channel requires a little bit of collateral by each party to open up in the first place. And then eventually each of those channels can finalize to the blockchain. And when that happens, the collateral is like opened up, and the net difference is handed back.
It's kind of like even out. So that answers my question. So there has to be collateral involved, because I was thinking like, okay, with the range proofs, I have to obviously make sure I'm within a normal range, but I also have to make sure I have the money.
For payment channels, you need collateral. For Mimblewimble, you need those commitments to be around so that you can open them. But just like for Bitcoin, if you don't wait for the whole confirmation period, you do run the risk of a reorg. And in fact, like that's always true. It's just maybe the probability drops exponentially or whatever. The idea is that this is Mimblewimble thrives in a situation where you have a bunch of off-chain transactions with relatively mutually trustworthy parties who occasionally want to settle to a blockchain.
Okay.
Does that make sense?
That is a lot more trust than I'm like. So I'm used
Even
to.
the
at least
fact that
in
it's supposed to be a trustless thing, I agree.
Yeah.
So Brandon, I think what you said is maybe what the original paper described, but I think how it's been implemented in places like Grin and Epic Cash is the miner actually performs the cut throughs in the sense that if person A sends to person B sends to person C, they can excise out person B. Because the money just ends up, all that matters is the money ends up to person.
Sure.
So from a implementation standpoint, it ends up not being like offline payment channels that eventually settle, and more being like, okay, these it ends up this way down the line, so we can cut out the center stuff. I don't know. So this is something we're gonna have to potentially look a little bit more into when we have time in our very limited amount of time. I do want to mention a couple of questions that have come through the chat. Like, is this protocol still relevant today? It seems like the state of the art on scaling has moved on. Under what circumstances is Mimblewimble still useful? And I had replied that, we're discussing this because there is an element of privacy to it with the cut through. And knowing all options in terms of privacy or, kind of increasing your general knowledge in the space can spur ideas in other areas. And ultimately what we're trying to get through with Mimblewimble is, Brandon did some work a year or two or maybe 3 or whatever ago for Epic Cash about potentially going to non-interactive transactions. And this is the stuff that is kind of important and interesting because, yes, I agree that Mimblewimble, the original paper as written, people have kind of moved on from that idea as they've realized that, the cut through is not as good, the privacy is not as good or whatever. But there are, if people build on this idea to do a sort of, like Brandon is saying, where you can go non-interactive, but at the cost of the cut through. Well, the cut through is also giving us problems in the sense that we are having to deal with no record of transactions. So maybe it's good to get rid of the cut through, right? If it also gets rid of the non-interactivity, although I don't know how that separates it from just regular Bitcoin at that point, because Bitcoin doesn't have cut through and it's non-interactive. So what benefit does it serve? Anyway, all these things, kind of to answer the question directly to the viewers, I think it's important that we look at all the technology that has come into space, especially things that we don't know, because who knows where that aha moment is going to come, right? Where somebody's like, wait, but if we just do this, right, then we can make things more scalable. We can make things more private. We can make things more whatever. So even stuff that seems fairly like, I'm not quite sure. As an example, Tari. Fluffy Pony moved on from Monero primarily and has been doing stuff with Tari. Tari has, or at one point had, some form of Mimblewimble. I think they might still, they might not. And that's on a docket for a future meeting, is kind of what Tari changed and what kind of Mimblewimble they are, if at all still. Yes, Brandon.
So getting back to how this is practically implemented and how the miners perform the cut through. So if you imagine like a long block time, like 1 month, which is ridiculous. But by the way, I love thinking about things like that. Like I would really like to start a cryptocurrency that moves at like a glacial pace.
Call it Glacier. That would be a good name.
Yeah, and then melt a glacier to run it. All the proof of work done in a month, just get 1 block. Anyway, if you think about it that way, then like the miners have this massive opportunity to perform as many cut throughs as possible, right? And if you look at the entire blockchain as like a transaction tree, then cut through applied to the whole blockchain, according to like the original Mimblewimble paper. I shouldn't say original, but Polstra's original description of it would reduce like a 15 gigabyte blockchain down to 1 meg. 15 gigs to 1 meg. Like that's ridiculous, right? but because you have actually short block times, and the cut through can only go block by block, what's the likelihood that a large number of cut throughs occur in a 10-minute block period? Like
Not
it's
large. Yeah.
it's not large. So the benefit that you gain from having cut through in Mimblewimble, in my opinion, just isn't there. If you have a storage constrained device or something, there are other ways to make things like reduce your bootstrapping cost and make things locally smaller while still allowing verification. And that leads me to this point, which is secure fountain codes, which actually Freeman's advisor is the one who pointed me towards this paper years ago. It's on pip, or it's on Pi. I mean, you can do pip install secure dash fountain in order to get my Python prototype for this thing. But it's essentially a code-based way of locally reducing your blockchain cost in a way that allows you to still perform transactions or transaction verification a lot of the time. And it reduces the amount.
Live streaming is on.
Okay, let me just double check it's all working. Sorry, guys. Maybe the Jitsi thing does very silly stuff there, has a 1 hour timer or whatever, which might make sense, but we'll go ahead and go forward from here. We're almost done. We're almost done.
So are we live?
We
Again?
are live again. Okay,
Okay,
go.
great. So anyway, you can do pip install in Ubuntu or any Linux, obviously. Secure dash fountain. And you can get my prototype code for secure fountain codes, which is a coding theory based way of it. Like basically you encode blocks locally as droplets, and you can serve up combined blocks as droplets to new nodes. And if they collect enough nodes or enough droplets, they can reconstruct a chunk of the blockchain in a verifiable way so that you can tell if the other nodes around you are trying to persuade or are like trying to lie about the contents, which is really sweet. And it's close to optimal. I don't know why I've been unable to. It's blockchain agnostic. I don't know why I've been unable to get anybody to use this thing. Maybe Kayaba could explain it to me. But essentially, this would allow light blockchain client verification, or light blockchain verification on storage constrained devices, and it's blockchain agnostic, which I think is really, really cool. And so there's other ways. So one of the questions that people in the crowd asked a minute ago, Diego, was haven't we moved past this sort of version of scaling? And the answer is kind of yes. This was my contribution to that. I haven't been able to get anybody to use it. There may be better code-based approaches out there, and Freeman and Luke would have a better idea about that. Do you guys have any comments about that?
When you say, like you mentioned something that sounded like Byzantine fault tolerance, is that what this looks like?
No, it's more like you're exploiting the hash chain to make sure that the people around you aren't serving you what are called murky droplets, which have been maliciously tampered with. Which is nice because basically, since you already have the hash chain, you may as well use it, and it's all XOR based, which is kind of interesting. Anyway, I don't have much more to talk about.
Yeah.
Other than I want to emphasize that the Fuchsbauer solution abandons cut through in favor of losing interactivity, which I think is probably a good choice. And so I'm not sure how much research has gone into Fuchsbauer's Mimblewimble stuff since my work on it my readings on it a couple of years ago, but I didn't get as far into that as I wanted to. What's up, Freeman?
Something I recall, it was actually a really nice paper. I'll see if I can find it. They were talking about interactivity with like Mimblewimble and Bulletproofs. They had like 30 different protocols that they were looking at. But the thing is that every single one of them did the non-interactive step in Fiat Shamir incorrectly, except for Monero. That was pretty much like it. Is they were all vulnerable to like Frozen Heart, weak Fiat Shamir stuff from like a protocol implementation standpoint. So I think that's something worth thinking about, is that like pretty much everybody who implemented Mimblewimble to some extent did it incorrectly. And that's probably been fixed retroactively, but it makes you think.
So we have Fiat Shamir like, or rather let's say non-interactive.
Almost Fiat Shamir.
Like just non-interactive, I guess. Implementation dangers. And I'm going to list Frozen Heart as one of the big ones because we know that one applies to almost everything. Like almost, yeah. That's pretty cool that Monero is one of the only ones. Do you remember which paper it was that you found that in?
I'll see if I can find it. It might take me a hot second. I know I've cited the paper like 5 different times, but
I see. Okay. Well, I have nothing else. It's been a pleasure, you guys. Is there anything else you guys want to talk about?
I'll outro us here a bit because
That's all.
we're hitting about the 2-hour mark. So it's a lot. We probably won't. Not probably won't. We don't have time to discuss kind of Brandon's readings because, like I said, Epic Cash hired Brandon to look into kind of the non-interactive Mimblewimble stuff some time ago and deliver something, and he did do that. I'm not sure if they ever published that or not. And so I wanted him to discuss kind of the non-interactive things that he has seen and potentially any more that have popped up on the horizon, if so, and what their benefits would be. No time to do that today, and we probably won't have time to do that before Stack Attack. But Brandon, you can go ahead and do that at Stack Attack.
Yeah, for sure. Do you guys want to stream stuff from Stack Attack? Is that part of the plan?
No, we're not going to be. So for those viewers, Stack Attack is when I get all my Cypher Stack people who all work remotely from various places, all into the same space for several days, so we could just do a whole bunch of math all at once. If you want to buy us pizza, please let me know. I'll accept the Monero and get the pizza for when that happens. And the next one is coming up very, very, very soon. At Stack Attack, I think we may have kind of a panel type thing, which I will publicize. We can all sit there and answer people's math questions. Maybe 3 people will show up and they'll have 2 questions for us total. And that's, we'll answer them and then that'll be that. But yeah, we're not going to be recording, screen anything, live streaming any of our Stack Attack stuff unless somebody's presentation or talk or discussion is so good we say we must get this out there to the world, which I like you guys, but I don't think any of you guys will make something that fantastic. So thank you guys for watching the live stream. It was kind of in 2 parts there where they discussed math stuff and I was bored out of my mind, and then they discussed Mimblewimble stuff and I was able to contribute somewhat with my real world experience. I hope it was fun somewhat. I know it's a bit mathy, but that's what these meetings are all about. So let us know if you liked it. Let us know if you want us to do this again. Or you could be honest and say, like, this was a neat thing to try, but I'll be honest, I would not watch more of these. That's fine. We won't get offended. These guys like the math, and that makes them all smiles. So that's all I need in my little boss heart, is to make sure these guys keep smiling. We'll go ahead and end the stream here. Thank you guys for watching. Let us know how you liked it.
Yeah, thank you very much.
Cheers. Thanks, y'all.